Okay, this is the solution to the higher level physics paper 2013 question 6. The first question is to state Newton's law of universal gravitation. I messed up, by the way, that's why I'm doing this handheld quickly. Here's Newton's law of universal gravitation. F is equal to g m1 m2 over d squared, where F is the force of gravity. Okay, g is our universal gravitation constant. Might be gravitational, I'm not sure. M1 is the mass of object 1, M2 is the mass of object 2, and D is the distance between the objects. Okay, so there's our formula that we're all hopefully very familiar with. The next bit was to explain what is meant by angular velocity. Not define, but explain. So what I've said here is the angular velocity is the rate of change of an angle, so tended by an object. It should be moving in a circle, actually. Let me just go back and write that. An object moving in a circle. I think that's better. It's theta over t. Okay, that's what we're trying to look for. The angular velocity is theta, the angle that is moved per second, per time. But it's an angle subtended by an object moving in a circle. We were then asked to derive an equation for the angular velocity. This is where I messed up a second ago. Okay, we know that the angle covered is s divided by r. I just drew a little sketch over here of something that's moving in an arc of a circle. We have s, the distance travelled, divided by r gives this angle here, theta. So the angle in radians is s divided by r, the distance divided by the radius of the circle. We want to know the angular velocity, so we do theta over t. So that means we have s over r, and that's divided by t as well, okay? But we know that linear velocity is s divided by t, yeah? Distance divided by time, that's fairly straightforward. We also know that theta over t is another way of saying omega. So you can see that this formula here has a v in it. S over t is there and s over t is there. So that's a v, and then it's been divided by r as well. Okay, so that means that my s over t gets replaced with an r, or with a v. There's still an r there, and we have omega, which is theta over t, which is the same as this thing, is equal to this thing here. Okay, omega is v over r. Okay, then for question part 3, you were given some information about the International Space Station, and we're asked to calculate its angular velocity and its linear velocity. Well, you're told its period is 92 minutes and 50 seconds. That means it does one full circle every 92 minutes and 50 seconds. In radians, one full circle is 2 pi, okay, 6 and a bit. So we have our 2 pi, which is our full angle covered, and it takes 92 minutes, 92 times 60, plus 50 seconds. So I'm putting it into seconds. 92 minutes in seconds plus 50, and you get this answer here, 1.128 by 10 to the negative 3 radians per second. Okay, so a small amount of radians every second because it's really far away. That brings us to the next bit, which is a little bit of a tricky one. Okay, the linear speed is omega r. We're rearranging this formula here. Okay, just multiplying both sides by r, so the linear speed v is omega times r. Bringing it back down here. There's my omega. It's the omega I just worked out right there a second ago. The radius now, this is the bit. This is the altitude, 4.13 by 10 to the 5, about 400 kilometers up. But it's also got the built-in radius of the Earth, 6.37 by 10 to the 6. It's not just the altitude. It's not circling about a point on the surface of the Earth. It's circling about the center of the Earth. So it's got its altitude above the Earth plus the radius of the Earth itself. That's my total radius of the circle that the space station is moving in. So this is the speed, 7 kilometers a second, 7.5 kilometers a second, which is pretty astounding stuff. Okay, that's part 1.